and get started. We'll probably have some stragglers come in. So my name is Emily Tanner Smith. I am the Associate Editor for the Methods Coordinating Group at Campbell, and I'm a Research Assistant Professor at Vanderbilt University. So we are video recording this workshop, so I am going to be relatively stationary here to stay close to the mic, so I apologize for that. So today this workshop is on using graphs for meta-analyses. So if you are supposed to be in the effect size calculation workshop, that is next door. So what I want to cover in this workshop first is really just to start by going over some basic graphing principles, and these are principles that apply to graphs that you would use in a meta-analysis as well as any kind of quantitative primary research as well. So just kind of situating ourselves in terms of good principles to use throughout all of your work. And then really what I want to talk about most of the time today is to go over kind of the three biggest types, or the three most common types of graphs that you would use in a Campbell review. So forest plots, funnel plots, and bubble plots. I'll talk briefly about some other types of graphs that might be commonly used in a Campbell review and talk a little bit about the software resources that are available for the different types of graphs, and then provide some recommended reading for those of you who are interested in more resources. So why do we have a workshop on graphs for meta-analysis? So it may seem like kind of a simple thing, right? But we see lots of bad graphs. You know, graphs are really important for conveying your research, and I think it's particularly important with systematic reviews and meta-analyses where some of our readers may not be quantitative or they may not have statistical training. So we may have policymakers and practitioners who are interested in the results of our systematic reviews. And honestly, they may go directly, you know, they may read your abstract, but they probably will look right at your graphs, right? Because that's what we look at. And so, you know, there is meaning to the cliche that a picture is worth 1,000 words, right? And so we can tell a very interesting story, a very powerful story with one graph, and convey a lot of information that might take pages of text otherwise to describe. So I think it's very important for us to think carefully and to really think systematically about creating our graphs and creating them well, because they do, that is kind of what your readers will latch on to. And so if they're created well, your graphs can convey a lot of information. But if they're created poorly, they can confuse your readers, they can frustrate your readers, and they can even be misleading. And I think that's particularly important for us to keep in mind with meta-analyses. So overall, the kind of general concepts, I think that any graph that you could create for a systematic review or for your primary research, it really should strive for accuracy first and foremost, of course, but simplicity cannot be overstated, clarity, and really good aesthetics. And I think it's this last one that is really difficult for many of us who are researchers, and we may not be trained in how to make an aesthetically pleasing graph, but that's actually just as important for conveying that information to your readers. So what I really want this workshop to do today is to help those of you who perhaps are already Campbell authors, or those of you who are thinking about writing Campbell reviews, to really give some guidelines for what really the methods group expects out of the graphs that you would include in your systematic reviews. And those of you who are maybe not Campbell authors or don't plan to be, I think most of these principles would apply for any kind of graphs that you would use for a meta-analysis in a journal publication as well. So let's start with some basic graphing principles. Now, some of these may seem quite simple, but I think too often we forget them. And so it really is worth reiterating. And again, these are principles that can apply to any graphs that you use to convey the results of a statistical analysis. So the first are descriptives, titles, and/or captions. So again, we all think, well, of course we put titles on our graphs, but it's very common to have titles that are meaningless to a reader. So really, you want the reader to be able to pick up a graph, look at it, read the title, and at least get some understanding of what they're looking at. So if I see a forest plot with a title that says forest plot of effects with 95% confidence intervals, what does that tell me? So what kind of interventions are we looking at? What kind of effects are we looking at? We need more information in that title. So your reader should be able to pick that up and at least get the general idea of what they're seeing in that graph. So that seems very simple, but I will tell you I see it all the time, to have very uninformative and kind of useless titles. So that's rule number one, I think. Second is the use of legends. So legends may not always be appropriate, but particularly with meta-analysis graphs. So if you're using different plotting symbols for different types of studies, it's important to have those legends that are labeled informatively so that your reader actually knows what's in that legend. That's very important as well. A third basic graphing principle is using a representative range of the scale. And so I think many of us can think back to our kind of introductory research methods classes where you show how you can present a very distorted picture of findings depending on how you present the results on a scale. So you can magnify a little bit of variability and make it look like a lot of variability by blowing out your scale, and you can also minimize some important variability by having very narrow scales. So it's very important to really have that representative range of scale for the graphs that you use for a meta-analysis. Of course, you always want to have properly labeled axes. Inclusion of reference points or reference lines on axes are important. So I think especially with meta-analysis, it's often useful to have lines at the null effect. Okay, so this might be a reference line at the 0 value if you're looking at standardized mean difference effect sizes. But often it can be useful to have reference lines at points that may be clinically or substantively meaningful. So if you've identified what effect might be clinically relevant, to have a reference point there. Again, to help draw readers' attention to those points. Now, for a meta-analysis graph, it is important for you to always explicitly mention if you've excluded data from those results, again, in the interest of transparency and replicability, just to be clear about any studies that you may have omitted for whatever reason. So perhaps if you've excluded an outlier, to have that, make sure that you've got that in a footnote. And then for systematic reviews and Campbell reviews, generally it's expected that all of the data that are presented in any of your graphs will be available in numerical form somewhere in your review. Okay, so if you've got your forest plot, your effect sizes and confidence intervals, if they're not actually on that forest plot, they should be somewhere in an appendix, in some of your tables perhaps. So that data should be somewhere where the reader can go find it. Again, the interest is in transparency and replicability. Now, I have a footnote here that except in very large reviews, so you may have we have some Campbell reviews that are very large, so we may have hundreds of studies that are included, and if we've got multiple effect sizes per study. So we may have situations where you've got thousands of data points where you might not include that in the actual review, but that's going to be a rare case. But I put that footnote there to recognize that there might be some situations where that's not appropriate. And then finally, aesthetics. So line thickness, I think, is very important. So it's important if you do have reference lines or have other lines on your graph to make sure that they are thicker than your axis lines, right? So these are basic principles. Using symbols that readers can actually see. Using symbol types that readers can actually see, and kind of parsimony and simplicity. And so this, I think, is the one thing I can't give you sets of rules, but it's really important for you to step back and say, what does this graph look like? Is it an ugly graph, right? Is it too complicated? I mean, really, you need to step back and think about that. And I have been guilty of this myself, to make a graph and, oh, you're so tired by the end of it, you've produced 50 forest plots, just plunk them in there. But really, that's doing your reader a disservice. And so I think really the basic, if you take anything away from this talk today, what I want you to take away is that you probably can't just use the defaults in whatever program you're using. It takes time to make good graphs. You often have to modify those defaults. And so just take a little bit of time, right? So we have to do that with our tables. Why don't we do that with our graphs? So many of the software programs, they have pretty good defaults, but often not good enough. You may have to make lines thicker. You may have to use different plotting symbols, things like that. So it takes a little bit of effort. Yes?
I was just going to say that with aesthetics, I'd be also with color, because so many times I've had a black and white photocopy of a report that says follow the blue line, the gray line, and I can't figure out which is which.
That is a fantastic point. So the comment was about color. And so that's very important, I think, in terms of aesthetics, is that if you do happen to use color in your graphs, you need to make sure that that will translate into grayscale. so that if you're using different colors, you probably need to be using dashed lines versus solid lines, or different plotting symbols, and don't just rely on color to differentiate, because really that should translate into grayscale so that readers who may not have it in color don't, because that can actually be quite misleading if an author or if a reader doesn't have access to that information. So that's a great point. Okay, so let's talk about forest plots. So forest plots, probably most of you, since you're in this workshop, are familiar with forest plots, but these are really the workhorse graphs of meta-analyses. So 99% of the meta-analyses that you have read probably include at least one forest plot. So most of us are familiar with these. So essentially the forest plot presents your effect size estimates and the confidence intervals around those effect size estimates from each of your studies included in your systematic review or your meta-analysis. And so typically, the way that we construct forest plots is to have each of those effect size estimates shown with a block that's proportionate to the weight that's given to that study. Okay, and so typically what that means is that the studies that have larger sample sizes, or which are providing more precise estimates of the parameters of interest, are getting more weight. And so we want to draw our readers' eyes to those studies, because really the reason that we do this is because you think about with forest plots, because they include the confidence intervals around these point estimates, that the smaller sample size studies that are less precise and have less weight in our meta-analysis have much wider confidence intervals, and so visually your eye would be drawn to those wide confidence intervals, but that's not really where we want our readers to look. We want to draw attention to those more precise estimates from those larger sample size studies that have narrower confidence intervals. So by having your boxes for each of your point estimates weighted proportionally to the precision, that draws the eye to those larger sample size studies. So typically with a forest plot, you've got your point estimates and your confidence intervals of your individual studies, and then typically if you've conducted a meta-analysis, you will have the synthetic mean effect size at the bottom, typically shown with a diamond. And if you're conducting a random effects analysis, I actually don't see this that much, but I'd like to advocate that people start doing it, is to include prediction intervals around your mean effect size estimates as well, because that also, when you've got heterogeneity in your data, provides more information about the variability and the predicted effect in perhaps the next study. Now, one thing that I want to implore that all of you who create forest plots is to think carefully about how you order the studies on that forest plot. So most software that you will use will probably default to ordering it by alphabetical order of the studies, or if you've got some study ID number, it may order it by that study ID number. And I will say that I know that many of the editors at Campbell, that is their pet peeve. Because if you've got probably more than 4 or 5 studies, often alphabetical order is kind of random, okay? And so it's difficult for you to visually assess, I think, heterogeneity if you've got point estimates that are all over the place and they're not ordered in any kind of meaningful way. So I would advocate that you try to order your studies on your forest plot in a meaningful way, and I personally prefer it when they're ordered by the effect size magnitude, because if they are ordered from smallest effect size to largest effect size, that does help the reader be able to visualize the heterogeneity or the homogeneity in your data and to see the range very clearly instead of having to look through all of the different studies in different ways. Now, there are other ways that you might want to sort your data on your forest plot. So you might want to sort by study weight or the precision of the effects. You might want to sort by chronological order if you wanted to look at the accumulation of evidence over time. Or there may be some other meaningful study characteristic. Perhaps it's a moderator of interest, and you may want to order your results in that way. So just again, think about these things. Don't just use the default that's in the program, because often that's not necessarily helpful to the readers. So what I want to do here is look at some examples of forest plots in Campbell reviews and just highlight some of the good things in these forest plots. So this is a forest plot from a Campbell review that was just published this year on interventions to reduce distress in adult victims of sexual violence. And so what you're seeing here are the results from a meta-analysis of 3 studies looking at PTSD symptoms for treatment versus control conditions, okay? And so these are the forest plots. Most of us are probably familiar. These are the ones that you would get out of RevMan. And just I want to point out a couple of good things about the forest plot here. So first, in our forest plot, we see what the effect size metric actually is. It's a standardized mean difference effect size metric. We all laugh, right? We think that's normal, but it's very common for people just to label their forest plots with effect size. What does that mean? There are 50,000 different types of effect sizes that you might be using. Now, we know in a Campbell review it's probably one of 3 or 4, but tell your reader what the effect size metric actually is. The IV here is just indicating that it's inverse variance weights that are used. The random is indicating that they're using a random effects analysis to pool the results. And then the 95% confidence interval, I think that's also important to note, because too often we will default to just perhaps assume that people are using 95% confidence intervals, but we can't assume that, because you might be using 90% confidence intervals, you might be using 99% confidence intervals. So it's important to indicate that to your readers when you are presenting results from confidence intervals, what your alpha level is. So here, because we've got standardized mean difference effect sizes, the results are centered around a null value of 0, but sometimes that may be centered around a null value of 1 or some other null value of interest. So it's important to have that null value. And then what I really want to point out here, and again, this is another thing that I often see, is a failure to tell your readers which direction your effect sizes are coded in. Is a negative effect size a good thing? Is it a bad thing? I don't know. And we all have different kind of ways that we typically code our effect sizes. I tend to code my effect sizes so that positive effect sizes are a good thing. So if this label were not on this axis, I might go and say, oh, there's a negative mean effect size. That's a bad thing. Maybe these treatments are having negative effects on PTSD. But no, we can see here that negative effect sizes indicate that there is a beneficial treatment effect. So it's very important to make sure that you label that axis, because that can have very important implications in terms of how your readers interpret your results. So just to point out here, so this is a small meta-analysis with 3 studies, but you can see here, again, we've got the green boxes that are proportionate to the study weight. And so you can see, that this second study here has a much smaller sample size, right? So we've got a sample size of 18, and that's why it's got this wider confidence interval, okay, because it's a less precise estimate of the parameter of interest. And we've got the smaller box versus the first study and really the third study where you've got larger sample sizes, and so those studies are getting more weight. So it's not as obvious in this example, but really, again, the point of weighting those boxes and sizing them proportionate to their weight is to really draw your eye to those larger sample size studies. And then we have our mean effect size down at the bottom there, okay? So here's another example of a forest plot from a Campbell review looking at truancy interventions for chronically truant students. And so this is a larger meta-analysis here, so we've got more studies. And so I don't know how this was created. I'm thinking it might have been done in Excel, but there are different options available to you. And so I just wanted to point out a couple of good things here. So first, we see that the effect size is labeled as a Hedges G, right? So we know what the effect size metric is. We know that they're using 95% confidence intervals. And this is actually a good example where you can see the importance of the weighting of the boxes to draw your eyes, because we have several studies here that have wider confidence intervals, and just normally your eyes kind of are drawn to those because they're taking up more space on the graph. But what I like about this forest plot is that, lo and behold, they have sorted the forest plot and sorted the effect sizes in order of magnitude. And so to me, this is very helpful as a reader because you can visualize the heterogeneity. In this example, it's heterogeneity because you can see that the effect sizes from the studies range all the way from 0 to 1.2, right? So that's a vast array of effect sizes there, whereas if they were all kind of randomly ordered, it might be a little bit more difficult for the reader to see that. And at the bottom, we've got the indication of which positive effect size is good in this situation. Okay, so what we just, yes?
Yeah, before we go, you mentioned that prediction interval is good and then it's very hard, but how can I produce that prediction interval?
Okay, so I am not a RevMan expert. Oh, so the question was, how do I get the prediction interval onto my forest plot? And so that will probably, how you get that done will depend on the software that you use. I'm not sure about RevMan because I don't use it on a regular basis if it's possible to get that. It might be something that you would need to calculate by hand to add to the forest plot. You can get those in Stata. I think you can get those with the Mix software. So some of the software systems will do that for you and automatically calculate those. I'm sorry?
Do you think it has a feature in CMA, the contrast manner?
So the question was, can you do that in CMA? And I'm not sure. But actually, if it's not there, then we should request that they add it. Because I would think that the authors of CMA are quite, they know about prediction intervals. They advocate us to use them. So I would guess that they would be inclined to at least add it if it's not there already. Yes. But you may have to do more work and calculate it by hand if it's not in the software that you're using. Okay, so what we just looked at were forest plots, the typical kind of forest plots where you've got one effect size for each of the studies in your meta-analysis. But there are actually lots of variations on forest plots that you might use in your Campbell review. So forest plots with subgroups, I think, are probably the second most common type of forest plot we will see. And so this is where you've got your forest plot like we just saw, but essentially you've sorted your study by some moderator or some covariate that's categorical, although you could actually use it with a continuous variable in some ways. And essentially have your forest plot grouped by the values of that grouping variable. And so this is often useful if you are conducting a moderator analysis, say in an ANOVA kind of framework, and if you wanted to compare the mean effect sizes across two or more groups. Now, there are some situations where you may actually be interested just in those subgroup effects, so you may not actually present the result for the overall mean effect size across the groups, and so that will depend on your review topic and your goals. But if you do conduct statistical tests for whether there are differences between those two groups, I do just want to highlight that you should include the results of that significance test somewhere in a footnote, for instance, in that graph. So here's an example of a forest plot with subgroups. This is fake data. I just made it up. So let's say that you were looking at, say, a tutoring, math tutoring intervention, and you wanted to see whether shorter kind of single session tutoring intervention programs were, had different effect sizes than perhaps the multi-session tutoring intervention programs. So in your data, you may have a dummy variable indicating whether it was a single or multi-session intervention. And so here in the forest plot, you can split your results, have your studies and their confidence intervals depicted for each of the two subgroups separately. And so in this forest plot, I don't have the overall mean effect size shown. Okay, so perhaps for some reason you have a theoretical reason or a substantive reason for not doing that. You may not actually include that overall mean effect size. So instead what you might have are just the subtotal mean effect sizes. And here you can see an example with the prediction intervals around your mean effect sizes. So if you were doing this in a random effects framework, that might be useful. Yes, so I just highlighted that. So here's an example where perhaps you might have the overall mean effect size included at the bottom. And so in this situation, presumably, you might be wanting to test whether there was a significant difference between the two groups. So it'd be helpful to have a footnote there with perhaps a meta-regression coefficient or a Q-between test if you're using an ANOVA model, having that information there in the graph for the reader. Because again, the goal is for the reader to be able to pick up that graph and really be able to get as much information as they can get without having to read your text. And so what that footnote would tell your reader is perhaps that there are significant differences so that the multi-session tutoring programs did have a significantly larger mean effect than the single session interventions. And you could have prediction intervals around your overall mean effect. I forget what I've got in there. Yes?
So does the size of the diamonds you has I mean, there are prediction intervals, of course, but normally the size of the diamonds also.
Yes, and so the question is whether the size of the diamonds for the mean effects is proportionate to the amount of information essentially that's covered in those effects. And that's a good question because Well, so typically, yes, the size of the diamond, so the edges of the diamonds, yes, sorry, if that's what you're asking, yes. So the edges of the diamonds will reflect the confidence intervals, and then these bands on the outside would represent your prediction intervals. And so your prediction intervals will always be wider than your confidence intervals because of if you've got heterogeneity there that's taking into account that between studies variance. Yes. Yes.
Is the size of the individual study effect size also meaningful? Sometimes we see that the dots have different magnitude.
Yes, and so the question was, does the size of the points for each of the individual studies have meaning? And yes, and so in this example, I made this data up, and it looks like I probably made the data up so that the sample sizes were all quite similar, because you can see that there's very little variability in the size of the box. But in actuality, when I ran this, they should be proportionate to the study weight. It just so happens that they all look to be similar here. Yes?
I don't know if you mentioned it, but I want to be sure if you look at the subgroups, are the effect sizes significantly different?
Right. So the question is, if you look at the subgroups, are they significantly different? So I can see situations where you may not actually be interested in comparing those two subgroups. But I would say probably in a lot of Campbell reviews, you actually are interested in comparing those subgroups. And so here, I would say if you do compare those, to indicate, at least in a footnote, to provide the basic information. So here, I just gave an example. If you used a meta-regression model with a dummy variable for treatment length, you might want to report that regression coefficient with the confidence interval indicating whether it was significant or not. It could also be a Q-between test from an ANOVA model to test for the moderator. So if you do that test for moderation, I think you should include that in a footnote.
Can you visualize that?
So the question is, can you visualize whether there's a significant difference? So the fact of the matter is, typically what people will do is compare the confidence intervals for the two subgroups to see if they overlap. That's actually not always going to be true. So it's quite possible that the confidence intervals will overlap, but there is a significant difference between the two groups. So you can visualize it kind of by looking at, if you've got a 0.32 that goes from 0.2 to 0.5, and down here we've got 0.6 that goes from 0.49 to 0.73. So here they're not overlapping, so you could visualize it that way, but there are some situations where they might actually be overlapping, but you have a significant difference between the groups. It's a great question. Okay. So the next variation on a forest plot I want to talk about is a summary forest plot. And so summary forest plots are essentially, they're taking bits of what we just saw with the subgroup forest plot, and essentially what you've got now are, you're no longer presenting the individual effect size estimates from each of the individual studies, but rather what's showing on the forest plot are those average effects for a given subgroup. Okay, and so the summary forest plots like this are going to be very helpful if you've got a large review where it's not feasible or it's not practical to do an individual forest plot like we just saw, because what if you've got 500 studies? You can fit that on a forest plot, but let's remember aesthetics. Okay, that's not going to look good, and it's not going to be helpful to your reader. So sometimes summary forest plots will be helpful, and especially if you do have a large number of studies, there probably are some different subgroups that you may want to classify. So it may be classifying by participant characteristics, perhaps age, or perhaps program variations, or variations by outcome type. So there are all kinds of situations where this might be appropriate to use a summary forest plot. Yes, and so again, kind of the same sort of rules apply. So if you do conduct significant tests to test for moderation across those subgroups, you would want to include those in footnotes, but you may not be interested in those effects. So here's an example of a summary forest plot. Again, this is fictional data that I just made up. And say we've got 500 studies all over the world, and so you may want to present the mean effect sizes across the different countries in which the studies were conducted, for instance. So here, essentially, you can see that these are just giving you those mean effect sizes, the diamonds that we saw in that forest plot with the subgroups, but you don't have the individual point estimates for each of the individual studies here. So we don't see these as commonly in Campbell reviews because we don't have a lot of very large reviews, but it's just something to keep in mind if you are doing a very large review. A summary forest plot can be useful. Okay, the final variation on forest plots that I want to talk about are cumulative meta-analysis forest plots. And again, we don't see these very often in Campbell reviews, but you can conceive of situations where it may be interesting. And so here, a cumulative forest plot essentially is structured in a forest plot format, but it's giving the reader a different picture, because essentially what you're doing is sorting your data in some order. And so typically that might be publication year if we think about kind of traditional cumulative meta-analyses. And then cumulatively estimating meta-analyses with the addition of each new study. Okay, so typically these would be used to display the accumulation of evidence over time, so the stability or instability of effects over time. And so the classic examples have been used to indicate, well, you know, if we've got this treatment that can help save lives, if we get to a point where we've got pretty consistent evidence that that treatment is effective, perhaps we don't need to go spend another 10 years conducting huge multi-site trials when we might actually have sufficient evidence for that. So we don't see this as much with Campbell reviews, but there might be situations where it could be useful to you. I've used publication year as an example of when you would do a cumulative meta-analysis, but you can also use it to actually look for small study or publication bias by accumulating effects over your sample sizes of your studies. But that's a whole other issue, so we can talk about that more if you're interested. So here's an example of a cumulative meta-analysis forest plot. So the first thing you should probably notice here is that the point estimates that you see they don't have boxes around them, and the boxes don't vary, right? And why is that? It's because this is actually a different type of a forest plot, because what you're seeing here, we've got our data sorted by year. So this point estimate here of negative 1.84 is the actual effect size from this Fletcher study. The next point estimate of negative 1.04 is the meta-analysis from the effect sizes from these two studies. The next one is cumulating across 3 studies, the next one across 4 studies, and so it's accumulating that evidence and calculating those mean effect sizes over time. So it doesn't make sense to include the boxes around those mean, because they're really mean effect sizes, so that's not just the effect of this one study. And so this is kind of the classic example where, you know, by the late 1970s, there was pretty consistent evidence of a beneficial treatment effect. But it wasn't until after these large randomized trials were conducted in the 80s that this treatment was taken up. So we don't see these as much, but it's an option available to you, typically if you're interested in the accumulation of evidence over time. Okay. So general suggestions about forest plots, and again, these are kind of suggestions for Campbell reviews. Hopefully we've kind of hit all of these, so they shouldn't be a surprise to you. So generally, you will always want to include a forest plot in if you conduct a meta-analysis or a systematic review for that matter. And so if you've got a very large review, perhaps it may not be appropriate to do kind of a traditional forest plot, but you may want to use a summary forest plot or something like that instead. Now, of course, you probably don't want to use a forest plot if you have fewer than 2 studies, because, right, then you can just report that in the text that you've got the effect from 1 study. For those of you, it's probably less common with many of our Campbell reviews, but if you do have binary outcome data and you're using, for instance, a log risk ratio or a log odds ratio, typically you will want to plot those effects on that log scale, but then include the tick marks on your axes in the ratio scale. That makes more sense to readers. It's good practice to always include reference lines at the null values to state your confidence intervals. For traditional forest plots, remember to always have those blocks proportionate to study weight. Again, please sort your studies in a meaningful order, okay? Don't just use the default author alphabetical order. Try to think about what will be useful for your readers to see. State the direction of your effect sizes. Include prediction intervals for random effects analyses if possible. And include numerical data on your plots if possible. And actually, one more thought about the prediction intervals. You know, if it was something that you had to do by hand and it was a really big pain to put it on your graph, it might be something you could report in the text at least, because then you could at least calculate it and not have to worry about putting it onto the graph. So I'm about to move on from forest plots. Any questions, thoughts, comments? Yes, Martina.
What are your recommendations for when meta-analysis is not possible because, say, your outcome measures are different, but you still want to plot them in a forest plot?
Right.
Kind of at least provide a general indication of direction.
So that's a good question. So the question was what I would recommend if you conduct a systematic review and you have effect sizes from studies, but you've decided for some reason that a meta-analysis may not be appropriate. And so in that situation, I think a forest plot can still be very meaningful, and so it can be useful to have that information there. The one thing is that you do have to be careful because readers will tend to want to do their own cognitive algebra to calculate the mean effect size, even if you don't present it to them. So you do kind of have to be a little bit wary about how your readers might take that information. But it can still be very useful in terms of presenting the results succinctly from all of the studies included in your systematic review. And I would say that if you do present them in a forest plot, again, use captions and footnotes to say, you know, a meta-analysis was not conducted for this reason. So that way, at least you have your disclaimer on there. And if a reader's going to take that and misinterpret it, you've done your due diligence. Okay, so let's look at some bad forest plots. I told you we were moving on, and I lied. I forgot I had these. Again, it's probably beating a dead horse, and I made these, so they're not anybody's bad forest plots. I made them specifically for pedagogical reasons. So there are lots of things wrong with this forest plot. So first, we've got kind of these uninformative study labels. So what is study number 1? I don't know what that means. I'm not in your data set. You know, tell me what that means, okay? So typically this will be an author and a publication year, right? That's going to be useful. But, you know, remember that there are other characteristics or other types of data or study characteristics you might want to include in the left-hand side or on the right-hand side as columns that might be useful for your readers. Here's a seemingly random order of effect sizes, although they kind of are in effect size magnitude. But again, you know, there doesn't seem to be any consistent sorting here of the effect sizes. There's not a clear direction of the results, so I don't know if mean negative effect size is bad or if it's good. So again, that's not helpful at all. We don't have the actual effect sizes and the confidence intervals presented anywhere in the data, so whether it's on the right-hand side or the left-hand side. Again, if possible, and if you can actually do that, it's good to have that on the actual forest plot or in the plot. So in RevMan, it will be kind of to the left. We don't know what level of confidence or the confidence levels for these intervals. And then the general aesthetics, you know, so there's a lot of white space in this graph, which is not very aesthetically pleasing. So, you know, play around with the options, try to, you know, maybe adding more text. I think by having study author names, study characteristics, your effect sizes, that would be helpful here. Now we're moving on. Okay. So let's talk about funnel plots. So I would say next to the forest plot, the funnel plot would be probably the second most common type of graph that we would use in a Campbell review. And so funnel plots really are kind of exploratory data tools that you can use to assess the possibility of small study bias or publication bias in your data. So this is not a lecture on publication bias, so I'm going to try to at least stick with the graphing. We can talk about it if you want, but typically with the funnel plot, what you're plotting is just a scatter plot, okay, of your effect size against a measure of precision. So typically that measure of precision will be your standard error. There are actually lots of different options for this, and Stern has a piece in 2005 that talks about the pros and cons of the different options that you could use for your y-axis. Generally, unless you have a compelling reason not to do so, we would recommend that you use the standard error of your effect size on your y-axis. And then on your x-axis, if you're using ratio measures, like a logged risk ratio or logged odds ratio, you would want to use those log scale values on your x-axis. Now, there are lots of situations where you probably will not use a funnel plot. Okay, so most of our Campbell reviews don't have funnel plots in them because they're typically not recommended if you've got less than 10 studies. They're typically not recommended if you have lots of heterogeneity in your data. They're typically not recommended if you have no significant studies in your data. They're typically not recommended if you've got all studies with similar sample sizes. But in many situations, they will be helpful for assessing small study bias. And so really the logic here, by plotting your effect size against its standard error, the logic is to look for symmetry or asymmetry in this funnel plot to see if there appears to be a relationship essentially between sample size and your effect size. So really what you're interested in is, does it appear that there are kind of missing studies that have small sample sizes with null or negative effects? And by negative, I mean opposite of what you would expect theoretically. And so the logic here is that large sample size studies, so these are studies that have smaller standard errors, they're more precise, they're more likely to get published because of the time and the resources and energy that have gone into collecting the data in this large sample size study. Whereas smaller sample size studies, which are generally less precise, we're giving them less weight in our meta-analysis, are more likely to be published if they've got significant results. Okay, so the logic then is that you may be missing these smaller sample size studies that have null or negative findings for whatever reason. So maybe the authors didn't want to report those results because they didn't think they would be interesting. Perhaps they couldn't get those results through peer review. Perhaps the editor didn't like them. There are lots of different reasons why that might happen. But these are the general assumptions that you're making when you look at a funnel plot and look at the symmetry or asymmetry in the funnel plot to assess for small study bias. And so essentially the logic is that if you do have a relatively symmetric funnel plot, so symmetric around the mean effect size, then that at least gives you some confidence that there may not be small sample or publication bias in your data. The rub with the funnel plots, right, is that if you've got asymmetry in the funnel plot, it could be due to other factors. And I think I've got those on another slide. So I just wanted to look at an example of a funnel plot in a Campbell review. So here, this is a review of school dropout prevention programs on school dropout effects. So we've got on the x-axis, we've got the log odds ratio effect size plotted against its standard error. And so you'll notice here the point estimates for each of the individual studies, and then we've got some reference lines that are helpful for the reader to look at and assess possible symmetry. So typically you'll want to include these to be centered around your fixed effect mean effect size. And many of you are probably thinking, why am I going to do that? I thought Campbell always tells me to do a random effects analysis, right? So you want to plot these around a fixed effect mean, because if you've got heterogeneity in your data, it's going to make this very difficult to interpret, because in a random effects analysis, right, you're giving more weight to those smaller sample size studies, okay? So that's not going to be useful when you're looking at this correlation between your effect size and the standard error. So you typically want to center these around your fixed effect mean, and it's useful to have the confidence intervals around here just because it gives you an idea of heterogeneity in the data. So in this example of this funnel plot, you can see really what you're looking for. And in this situation, see, I've got a bad graph. It's not telling us which side favors which. But really, the null or negative findings would kind of be in this lower corner here. But you'll see that here that we actually don't have any small sample size studies that have positive effects either. So it's relatively symmetric in this situation. Now, you will notice with the funnel plots that the point estimates for each of the studies are all the same size. Right, so we don't have them proportionate to the study size, and the reason is because the precision of the study results is reflected in this axis here, right? So that's reflected in our standard error. So as long as we've got that precision reflected somewhere on the graph, we're good. So we don't need to have the plots being different sizes. Here's another example of a funnel plot in a Campbell review. for legitimacy and of policing. So again, we've got these funnel plots with the log odds ratio plotted against the standard error and centered around a fixed effect mean. Now, I mentioned this briefly, and again, this is not a talk on publication bias, but the problem with funnel plots, so they're good, they're helpful in many situations, but the problem with them is that what do you do if you've got asymmetry or if you think you see asymmetry? And you can't just conclude that there's publication bias because the asymmetry could be due to a whole host of other factors because study sample size could be confounded with methodological quality, it could be confounded with the risk level of the participants, it could be confounded with other reporting biases, it can be confounded with the type of effect size metric that you're using. So unfortunately, asymmetry doesn't actually always mean that you do have publication bias. And assessing symmetry is a completely subjective task, right? What I see as symmetric, you may see as asymmetric, right? And vice versa. And so fortunately with Campbell reviews, because we don't have the page restrictions that you might have in a journal publication, that's why we typically recommend if you do a funnel plot, please report it because it is subjective. And so we'd like the readers to be able to assess possible asymmetry themselves. Now, I realize if you're reporting in a journal article, you may have space limitations. And so I would encourage you in that situation, if you don't have the space, to at least try to include it as an online appendix or some extra material that you could have available to readers, just in the interest of transparency to do that. Now, there have been some improvements in funnel plot graphical methods that have tried to address this issue that any asymmetry that you see might be due to factors other than publication bias. So contour enhanced funnel plots, I think, are one way to try to get at this. And essentially, these are just funnel plots that have added contours or colors added at nominal levels of statistical significance. So typically at kind of 0.01, 0.05, 0.10 levels of statistical significance. And so the logic is that if you've got asymmetry, you can assess whether your missing studies or potentially missing studies are in the areas of significance or not. Because the logic is that if you're really missing studies in the areas of non-significance, you may actually have some publication bias. Whereas if it looks like the only studies that you're missing are in the areas of statistical significance, or if you've got kind of a combination of both, then there might be other factors associated with this relationship, and it may not be publication bias that's happening. So the contour enhanced funnel plots, I think, are one way that might help your readers assess whether the symmetry or asymmetry that you're seeing is due to publication bias. So here's an example of a contour enhanced funnel plot. And so this was made with Stata. And so you can see here that the outer regions, right, so the darker regions of gray are your areas of statistical significance. And so what we can see when we look at this plot is to assess, okay, what if we look at how symmetric this plot is, where does it look like we're missing studies? So it looks like you might be missing some studies in the area of non-significance in the white area, but you also might be missing some in the areas of statistical significance as well, okay? So this is an example where perhaps the asymmetry that you see could be due to factors other than publication bias because you're missing studies in areas of significance as well as non-significance. So we don't see these as much, but I think they can be useful. And if you do actually see that you've got some asymmetry in your funnel plot, it might be useful to use one of these. Okay, general suggestions. Funnel plots aren't recommended with fewer than 10 studies because it's difficult to assess symmetry or asymmetry with fewer than 10 studies. I should probably also say they're not recommended if you've got a high amount of heterogeneity. They're not recommended if all of your studies have the similar sample sizes. And they're not recommended if you have no studies with significant effects in the first place because they can be misleading in that situation. In general, you want to plot your effect sizes on the horizontal axis and the standard error of your effect sizes on the vertical axis. All points should be the same because the precision is reflected in that y-axis. It's useful to have your fixed effect mean, reference line, and some 95% confidence intervals around there because that really helps readers look at and assess the symmetry. And again, Actually, I didn't mention this, but something that you can do with funnel plots that can be useful is that if you do have a grouping variable that you think might help explain some of your asymmetry, you may actually use different plotting symbols for the different types of studies. And that can sometimes help you explain, like if you, for instance, if you conduct a review and you've included RCTs in quasi-experimental studies, maybe you think that the asymmetry that you see is due to the quasi-experimental studies, you could use different plotting symbols on your funnel plot to assess whether it appears that there was perhaps symmetry in your RCT studies but not in your quasi-experimental studies, or vice versa. So you can definitely do that. That can be useful for exploring possible reasons for asymmetry. Okay, so what's wrong with this funnel plot? So the first thing that I would say that's wrong with this funnel plot is that essentially we've got the effect size and the standard error kind of flipped. Now there's nothing wrong with this, and in fact some people will create funnel plots like this because it's easier in some software systems. So there's nothing wrong with this, but because you've got the effect size on your vertical axis, it sometimes can be misleading to people because they're not sure where they're supposed to be looking for the symmetry. They're not sure where they're supposed to be looking for the gap. Because really, if we kind of flip it like this is what we really are used to seeing, so we've got that inverted funnel. So there's nothing wrong necessarily with switching the axes like this, but I think it's good practice to have your effect size on your horizontal axis because readers are typically now getting used to seeing that and knowing where to look for that gap. So here I've made the points not all the same size. Okay, so remember again with a funnel plot, you don't need to do this because the precision of those estimates is reflected in the standard error, right? So the larger standard error studies are giving us less precise estimates, and that's reflected there, so we don't need to have your points be proportionate to the study weight. The value labeling of the axes and reference lines, again, what effect size this is, I don't know, right? So that's one of my pet peeves is when people just say effect size, right? There's so many. So this is not, these axes are not labeled well. We don't have confidence bands around that fixed effect mean. Oh, I guess that was all for that one. So just some ideas there for funnel plots. So any questions about funnel plots? Yes?
Just a question on the 10-study minimum. So our review has 102 studies,
Yes.
but we only have 5 of our outcomes that have 10 or more studies for those outcomes. So does that hold for just doing for those 5 outcomes, or?
So the question is, they have a lot of studies, but a lot of different outcomes, and some of the outcomes, or most of the outcomes have fewer than 10 studies in them. And, you know, that's a good question. So one approach that you could use, well, so I definitely would do the funnel plots for the ones where you do have at least 10 studies. I mean, there's no reason not to do it for those outcomes. For the other outcomes, well, yeah, so how many studies do you have in those?
Range from, 5, 11 or 5 or 6.
Right. To be safe, I would just stick with those outcomes where you do have more than 10 studies. One approach that you could use is to plot them all on the same funnel plot and use different plotting symbols for the different outcomes. But that's kind of misleading because you've got studies contributing more than one effect size. So I don't think that I would necessarily recommend that. Now, if you see consistently symmetric or asymmetric results for your studies where you can do the funnel plots, then that can at least be somewhat encouraging that hopefully there's not publication bias present for the other outcomes. If you see wide variability across those outcomes, then that's something that you can at least address in your conclusions when you're discussing the implications of your results. Other funnel plot questions? Okay. So do I have until 11:45? Is that what we have? Okay. So I'm going to fly through the rest of this. The forest plots and the funnel plots are really what you're going to be using the most commonly. Bubble plots are something we don't see that much in Campbell reviews, and I kind of wish we saw them more because they're very helpful if you're interested in questions of moderation, particularly with moderating effects of continuous or perhaps ordinal variables. And essentially, a bubble plot, that's just a fancy way of saying it's a scatter plot, between your effect size and your covariate, right? So we're used to seeing these in primary studies all the time, where you've got your study covariate on your x-axis and your effect size metric on your y-axis. And the only thing that's really different here is that because we're doing a meta-analysis, we want to make sure that we do have the points for each of those studies proportionate to their study weight. So bubble plots are very useful when you're looking at moderator analyses. Typically they would be used for a bivariate moderator analysis, but there are ways for you to use this in a kind of multivariable regression, meta-regression framework as well. So here's an example of a bubble plot. So say you were interested in, I think these data are the effects of exercise interventions to help reduce depression. And so you might want to look at whether the duration of the follow-up is correlated with the effect size metric. Presumably, I would think you might theorize that the longer follow-up you'd see you'd see the effect size getting smaller over time. And so because of the way these effect sizes are measured, zero effect means that the treatment didn't have good reductions in depression. So again, here if you plot your symbols, so each of those circles are your study's effect size, and so they're proportionate to the study weight here because we don't have precision anywhere else in this graph, right? So we need to make sure that's represented somewhere. And then we've got a fitted meta-regression line here. So that might be from a bivariate meta-regression predicting your effect size with your duration of follow-up. Now you can improve on bubble plots and make them really fancy. So you might include that prediction line along with confidence intervals around that prediction line, so that can be very helpful for your readers to see whether effects are significant at different values of your covariates of interest. You might want to show predicted effects here if you wanted to show kind of residuals in your regression lines. So there are lots of different ways that you can use bubble plots like this. This is just kind of the bivariate context. We don't see these that much in Campbell reviews, but I think there are often situations where we are interested in ordinal or continuous moderators. And so, you know, this picture can be a lot more informative to a policymaker or practitioner reading your review than, say, a regression table. Right? I'm not saying that you shouldn't have that information in a table somewhere, but the figure can be very useful, one-stop shop to look at how duration affects treatment effects, right? So this can be very useful. I'm going to kind of skip through this. Kind of many of the same suggestions apply to the bubble plots. Again, just making sure that we've got the precision of the results somewhere in that plot. So we need to make sure that the plotting symbols are proportionate to study weight, and all of kind of the general suggestions apply. Two other graphs that you might use conceivably in a Campbell review. So one is a Galbraith plot or a radial plot. And so these are useful. You don't see them that much, but they're very useful in large reviews where a forest plot may not be practical to do. And essentially what these are, they're scatter plots again, but what you're plotting is the inverse of the standard error of your effect size against a standardized measure of your effect size. So typically your effect size divided by its standard error, so really a z-score. And so typically in a Galbraith plot, what you will see is you'll have this scatter plot, but you'll also have a fitted unweighted regression line constrained through the origin of the plot, and the slope of that line is going to indicate the fixed effect mean in your meta-analysis. And really the Galbraith plots are useful for displaying heterogeneity, and they're really good in large reviews where you may not be able to fit all of that information onto a forest plot. So here's an example of a Galbraith plot where we've got the inverse of our standard error on the horizontal axis, and then kind of our z-score, the effect size divided by its standard error on the y-axis. And so here, the way that these are fit, we've got our regression line fit here, which is essentially the slope of that regression line is going to be equal to your fixed effect mean. We've got confidence bands around that fixed effect mean. And the way that this scatter plot is formatted is so that the more precise estimates are going to fall farther from the origin, right? Because these are the studies that are more precise, whereas those that are closer to the origin are going to be the less precise studies, okay? And so you can get a feel for variability in effects by looking at that and then looking at the vertical scatter around that fixed effect mean regression line. So really that can be used to illustrate heterogeneity, because if you've got lots of points out here or down here outside of those bands, it indicates that you've got some heterogeneity in your data there. So this can be useful because it's really displaying the same type of information that you get in a forest plot, but you can see how you could include hundreds of points here that you might not be able to do on a forest plot. Okay. So the last type of graph that may be useful for those of you who have binary outcome data are a Labbé plot. Typically these would be plotting control group versus treatment group risks. If you've got binary outcome data, that's typically what I think about using them for, but you can actually use them for lots of different effect size metrics. You might actually use them for risk ratios or odds ratios. You can actually use them to plot means of your treatment group and your control group against each other. But they're really useful. Often you will see them to use contrast different effects using different effect size metrics. But I think in a Campbell review context, you might use them if you've got binary outcome data, because essentially this is what they look like. Again, they're scatter plots. And so here, if we've got our treatment group risks versus our control group risks, and if we have kind of a null line fit through the middle, essentially what this plot is telling you is that each of the studies that are above the null line indicate that the treatment risk was better than the control, whereas those below indicate that the control group did better. So here, again, the plotting symbols are proportionate to the study weight because that information on precision is not represented elsewhere. But this can be a nice way to kind of visualize the overall effects if you've got binary outcome data. We don't see it that much, but it's there and you can use it. I've only scratched the surface on the types of graphs that you can use in meta-analysis, and really I wanted to talk about the ones that we most commonly would use in a Campbell review, but there are lots of other graphs that you might use, and here are just a few of them. So if you're interested in some of these graphs, I've got some recommended reading at the end of this, at the end of the slides, or you can email me or come talk to me. There are lots of options available to you, and I don't think that we actually make use of these graphs that well. We kind of get used to just using the standard ones. So there's a lot more out there I have not covered. Software, we talked about this a little bit. So CMA, OpenMeta-R, RevMan, SAS, SPSS, and Stata, I think, are kind of the big ones. I've kind of modified this graph from an InPress article that I would highly recommend reading, talking about the use of graphs and systematic reviews and meta-analyses. And the authors there talk about different options in different software systems, so that the green checks indicate that you can make those graphs in those software systems, and the red indicates that, as far as I know, you cannot. Now, I will say that the green checks, that doesn't necessarily mean that it's easy to do it in that software system, but you can. Yes, so I will say that there are different levels of ease, and so it is kind of learning to work with what you have, but also realizing that there may be better options out there. And I would say that Mix, R, and Stata tend to have, I think, the best capabilities for doing the graphs. And I mean, because they're open source software, it's great because we've got wonderful people who are contributing packages to help us do this. But I'm not advocating any of those. You can definitely do a lot of these in SPSS or CMA. You may not be able to get prediction intervals, but you can at least get the general graphs. Okay, so just to sum up, graphs are really important when you conduct a systematic review and a meta-analysis. And so it's easy to kind of overlook them because at the point where you're making them, you may just be so fed up with your data, you just want to get rid of it. But really, your readers are going to latch on to the graphs. And so take a little bit of time, make them useful, make them informative, kind of always strive for these goals of accuracy, simplicity, clarity, aesthetic appeal, and just general good structure. So hopefully what we've talked about today can give you some general guidelines, but of course, every review is different, and so different things will come up in your own work. But really, it takes time and it takes effort, and you can't just use the software defaults. So, thank you. Yes. And here's plenty of recommended reading if you're interested in this, and of course, Actually, this is the Campbell email that you're welcome to email me at personally as well, or we've got 5 minutes for questions, I think. Yes?
So folks who have used RevMan, how easy is it to fix the default settings for the funnel plot? Is that pretty straightforward?
I'll let someone answer and then repeat it. Do we have RevMan users? So the question is, for RevMan users, how easy is it to change the default settings? And I must admit that I don't know the answer to that. But we can get you hooked up with someone who does know that, because it may be difficult to tweak some of those.
You look around for a guy named Sean Grant. He's the managing editor
Yes.
in my group, and he is a RevMan user.
So Sean Grant, the managing editor of the Education Coordinating Group at Campbell, is a RevMan user, and he's a graph expert, so he'd be a good person to talk to about that. I'm admittedly a Stata user, so I know more about that. We've got CMA users in the room. I know we've got to have an R user. I know we did good about kind of taking questions as they came up, but you're probably all hungry. So thank you for being here, and yes, just come talk to me if you've got questions you want to talk about one-on-one.